Good morning. Please check audio and video. In the last class, we were studying about the simple cubic crystal structure, and I told you that in a particular cubic crystal structure, atoms can be arranged in different ways. So the first way is atoms are only at the corners of the cube. This is known as simple cubic crystal structure, a simple cubic crystal system. Generally, this crystal system is observed in manganese, polonium, fluorspar. These are the important materials. Atoms are located only at the corners of the cube. Coordination number, it is defined as the number of nearest and equidistant atoms with respect to any considered atom. So you take any atom as reference atom and try to calculate the nearest number of atoms. Then atomic radius, you can calculate from the diagram, that is equal to A is equal to 2R, where R is atomic radius. Effective number of atoms. Each corner atom participates in 8 identical cells. So in a particular cell, its contribution is 1 by 8. There are total 8 atoms at the corners. So 8 into 1 by 8, that is 1 atom per unit cell. And then the next one is atomic packing factor, that is atomic packing efficiency. It is calculated as sum of atomic volume in a unit cell divided by volume of a unit cell, and that can be written as n is effective number of atoms and volume of an atom is 4 by 3 pi r cube divided by a cube. So for simple cubic crystal structure, n is 1, a and r are related as r is equal to a by 2. Putting this, we get 0.52. 0.52 means 52%. It means 48% volume is void. Now we will be proceeding for the next crystal system, that is body centered cubic crystal system. Body centered cubic crystal system. This is popularly known as BCC. Example for BCC are alpha iron. The iron which is found at room temperature, that is known as alpha iron. Molybdenum, tungsten, chromium, etc. Molybdenum, tungsten, chromium, etc. There are 8 corner atoms. 8 corner atoms. 1 at each corner. There is 1 atom at the center of the cube. There is 1 atom at the center of the cube. Center of the cube. There is 1 atom at the center of the cube. Let us make the cube. This is our cubic unit cell. This is cubic unit cell. So there are atoms at each corner. There is 1 atom at this corner, 1 at this corner. So at each corner there is 1 atom. So there are 8 corner atoms. Let us name these corner atoms: A, B, C, D, E, F, G, H. There is 1 atom at the center of the cube. So let us name it as I. center point should be at equal distance from each corner. Center means obviously the point which is at equal distance from each corner. So in fact, center atom is at equal distance from each corner. So if you consider center atom as the reference atom, then there are 8 neighbors, 8 corner atoms are the nearest neighbors. So in this case, determining coordination number is the simplest thing, because I consider this atom as reference and all the corner atoms are at identical distance, they are at equal distance. So there are 8 corners, coordination number is 8. So first parameter, if we want to calculate coordination number, that will come out as 8. That is the first parameter 1. Coordination number Cn. So BCC में Cn is equal to 8. Now we want to calculate the atomic radius. To calculate atomic radius, let us see this figure again. Dear friend, if you see, A and I will touch each other because they are the corner atoms, corner and center, and this I will touch F also. So A, I and F are in the same line. This H is backside. Okay. Similarly, E and I and D are in the same line. So if I draw this, let us suppose this is I, this is I. So A is touching to it, means this is A, and similarly F is also touching to it, so it is F. A, I, F. E and I are also touching to each other, so this is E and I. So now we are having this A, I, F and E, right? So AF you see in this triangle, this is R to R plus R, R to R plus R. So AF is 4R. What is F of E? F of E is dimension of cube, that is A. So FE is A. What is AE? AE is this dimension you see. This angle of cube is 90 degree. So in triangle ABE, AB is A, dimension of cube, and BE is A. So AE can be calculated. In triangle ABE, AE square is equal to AB square plus BE square plus BE square. So AE square is equal to AB square, that is A square plus A square. So this AE square is 2A square. This is AE square. Let's try to consider this triangle. In triangle AFE, in triangle AFE, AF square is equal to AE square plus FE square. AF square, that is 4R square, is equal to 2A square, this, and plus FE A square. So from this we can calculate R is equal to root 3 A by 4. This is the atomic radius, relationship between atomic radius and lattice parameter for BCC. Now suppose we are wanting to calculate effective number of atoms per unit cell. Third parameter, effective number of atoms, effective number of atoms per unit cell, atoms per unit cell. So if I calculate effective number of atoms per unit cell, N is equal to, still each corner atom will contribute 1 by 8. So there are 8 corner atoms, so they are contributing 1 by 8. So this is 8 into 1 by 8. Along with this, we have one more atom. These are the corner. Along with this corner, we have one center atom. Center atom is entirely within this cube. So it is not shared in any other cube. It is only in this cell. So this atom will contribute 1 to this cell. It is completely within this cell. So its contribution is complete. That is equal to 1. So 8 into 1 by 8 plus 1. This one because of center atom. So n is equal to 2 atoms per unit cell. 2 atoms per unit cell. This is the effective number of atoms. Now the last parameter is atomic packing factor. The fourth one is atomic packing factor. Atomic packing factor. Packing factor. This is popularly known as APF. This APF is sum of atomic volume, that is n into 4 by 3 pi r cube divided by a cube. So APF is equal to, n value is 2 into 4 by 3 pi into root 3 a by 4 का cube divided by a cube. So APF is equal to 0.68 या 68%. This is APF. This is APF. So it means it is more packed than simple cubic. Here 68% volume is occupied by the atoms. So this is all about BCC. Please note down quickly. Ritvik, this is the first heading, BCC. Today I started the class with BCC. Drishti, this is the first topic we started today. AF, we are taking AF to calculate the radius. R, you see this A and I touch each other, I and F touch each other. Similarly, you can take this also, E and I touch each other, D and I touch each other, you can take this corner. So any diagonal you can consider, and according to that you can do the calculation. कहीं से भी मन करे, periodic structure है, so you can calculate with any method. Yes, it is the first slide. Akash Rajput. Please do it quickly. Time से join करा करें भाई class. Abhishek Nagdeshi is saying that I am from mechanical branch. Can I skip? Yes, you can skip today's class, because mechanical students may have already read this. So those who belong from mechanical branch, they can skip this class. They may have studied this in their technical syllabus. Today we would be completing this chapter. So this chapter you can skip. You can join tomorrow onwards. Tomorrow onwards things will be new for mechanical student also. So mechanical people can skip this. They have read all these things. Yes, Omkar Sahu. Mukul, we are not calculating planar density. We are calculating in 3D. Plane is basically the 2D geometry, right? We will be talking about the planar density also. So, in a particular plane we would be talking later. This we are talking in a cell. Cell means 3D volume. Good morning, Manoj. Shall we go ahead? Dhiren, this we are calculating for each cell. What is the contribution of one atom? What is the contribution? What is the effective number of atom in a cell? That's why we are saying that the corner atom is contributing only 1 by 8. So, this effective number of atoms we have calculated in a cell, that's why it is written as per unit cell. In each cell you would be getting the 2 atoms effectively. Although there are 9 atoms which seems to be contributing, but out of these 9 atoms, 1 is completely within the cell and remaining 8 atoms are only 1 by 8th part. So, this way we have effectively 2 atoms in a unit cell. जल्दी करें, आप लोग यार लेट ज्वाइन करते हो, फिर उसके बाद एक ही स्लाइड पर रोके रहते हो. Do it quickly. Shall we go ahead? Good. Next we will be studying face centered cubic crystal structure. Next is face centered cubic crystal structure. Very important. Face centered cubic crystal system या structure जो भी लिखना चाहे. This is FCC. Very important. First of all, let us see the examples. Examples are silver, gold, platinum, nickel, copper, aluminum, lead, etc. Very important materials are there: silver, gold, platinum, nickel, copper, aluminum, lead, etc. There are 8 corner atoms. 8 corner atoms. 8 corner atoms. 1 at each corner. 1 at each corner. There is 1 atom at the center of each face. So there are 6 face atom. In a cube, how many faces are there? 6. जिस भी कमरे में बैठे हुए हैं उसे cube मान लें. So you can count 1, 2, 3, 4, 5, 6. So there will be 6 face atoms. There are 6 face atoms. 6 face atoms. 1 at the center of each face. 1 at the center of each face. There are 6 face atoms, 1 at the center of each face. Let us make the cube. Cube बनाते हैं. This is our cube. This. Like this. So there is 1 atom at this corner, 1 atom at this corner, 1 at this corner, 1 at this corner, 1 at each corner. So there are 8 corner atoms. There will be 1 atom at the center of each face. Now you see, my dear friend, this face atom is top face of this cube, then it will be bottom face of upper cube also. So each face atom is participating in 2 cells. So in a particular cell, its contribution is how much? Half. You see, half this is in this cell and half in the cell above to this. So each face atom will contribute in 2 identical cells, hence its contribution is 1/2 in each cell. अभी लिखेंगे बाद. How many faces are there? 6 faces. So there are 6 face atoms like this. Like this. Here you can show 2, 1 for front face and 1 for back face. If I make the front view of this face, किसी भी face का front view बना लीजिए. So 1 atom is this face atom, 1 this corner atom, 1 this corner atom, 1 this corner atom, 1 this corner atom. This would be the front view of any face. किसी भी face का front view बनाइए. You would be getting like this. Now you see, to connect these centers, this is A, B, C. Let us see. So AC is equal to R atomic radius, then 2R and then R, 2R and R, that is equal to 4R. What is AB? AB is this line. This line is what? Dimension of the cube, A. What is BC? BC is this line. This line is dimension of the cube, A. Now let us try to calculate the several parameters. सबसे difficult है इसका coordination number calculate करना. Have a look. Coordination number. For FCC. Let us consider the face atom as the reference atom. So if I consider the face atom as reference atom, then you see this face atom. So one atom this, one atom this, one atom this, one atom this. There are 4 atoms in the same plane in the corners who would be touching it like this. Then if you go up plane, corner cannot touch it, but the side, this side face atom will touch it, this side face atom will touch it. एक एग्जाम्पल से देखते हैं, ऐसे देखते हैं, एक बुक ले लेते हैं. Have a look in this book, right? Let us suppose it is a plane of a cube. Cube कैसे होगा? There would be one dimension like this, one like this, one like this, one like this, and one like this top, right? Now I am considering this bottom plane. So in the bottom face, you have one face atom. So in this plane, you see this corner is touching, this corner atom is touching, this corner atom is touching, this corner atom is touching. So there are 4 corner atoms which will be touching to this face atom. Now come to this plane. Suppose we go above the plane, then this corner cannot touch to this face. आपका face atom ये वाला है, लेकिन ये face इसको touch करेगा. This face will be able to touch this. Similarly, this face will be able to touch this, this face will be able to touch this, this face will be able to touch this. So there are 4 atoms in the top plane, right? Now you go in the bottom plane, your atom is this, but if you go below this, this face would be touching, this face would be touching, this face would be touching, this face would be touching. So there are 12 atoms, 4 within the same plane in which you are considering the atom, 4 above the plane and 4 below the plane. So in total there are 12 atoms. समझ में आया तो ठीक, नहीं आया तो रट लीजिए क्योंकि एग्जाम में पूछा जाएगा. So there are 12 atoms nearest members in the FCC. Then let us come back to effective number of atoms. Second one, yeah, radius. First let us calculate atomic radius. Atomic radius. Atomic radius. If I consider this triangle ABC, then I can write AC square is equal to AB square plus BC square. So in triangle ABC, AC square is equal to AB square plus BC square. AC square is 4R का whole square, A का square plus A का square. So it is R is equal to root 2 A by 4. You can also write as 2 root 2 R. You can write A is equal to 2 root 2 R. This is A. This is atomic radius. Now let us calculate effective number of atoms per unit cell. Effective number of atoms per unit cell. Corner atom still contribute 1 by 8, but each face atom participate in 2 identical cells. So its contribution in a cell is 1 by 2. Each face atom participates in 2 identical cells. Hence its contribution in a cell, is 1 by 2. So n is equal to 1 upon 8 into 8 plus 1 by 2 into 6. How many faces are there? 6. And each face is contributing 1 by 2. So 3 plus 1, that is 4. So n is 4 atoms per unit cell. 4 atoms per unit cell. This is the value of n. Now you see, once you have calculated effective number of atoms per unit cell, you can go for APF, atomic packing factor. APF, atomic packing factor. Sum of atomic volume n into 4 by 3 pi r cube upon volume of the unit cell. So n APF is equal to n into 4 by 3 pi r cube divided by a cube. So APF is equal to n is 4 into 4 by 3 pi into r. R is what? R is root 2a by 4, root 2a by 4 का cube divided by a cube. So from this APF is 0.74 या 74%. This is your atomic packing factor. This is atomic packing factor. Not answer, we are not doing any question. This is atomic packing factor. So frequently asked in the examination. Come back. This is all about FCC, face centered cubic crystal structure. Please do it quickly. जल्दी करें. Done? यस मनोज, बिल्कुल सही देखा आपने. इसकी पैकिंग एफिशिएंसी हाईएस्ट है. There is one more modified version of FCC that is found in diamond. So that is known as diamond cubic crystal structure. I am not going into depth of that structure, not going to calculate anything, just will be telling you the datas. उतना ही जरूरी है. That you can refer the calculation and geometry, all this you can refer from the theory book. As I told you, for some topics you need to refer theory book also, but briefly I would be wanting to talk about that. So इतना detail में calculation नहीं करेंगे, लेकिन फिर भी कुछ बातें जरूर करेंगे. So next one is diamond cubic crystal structure. Diamond cubic crystal structure. This structure is found in diamond, as the name is suggesting. Along with the diamond, it is found in some other fourth group elements also, like diamond, silicon, germanium, etc. They exhibit the same structure. It is also a cubic in itself, and there are atoms. बेटा कितना ढंग से आपको समझाया, फिर भी Mathons, Mr. Mathons, you see, this is a face atom. Let us suppose this is a face. So it is the face of this cube, top face. इसके ऊपर वाले क्यूब का क्या होगा, ये bottom face होगा, ठीक. So this is contributing in two cube, one this and one above this. So what is its contribution? 1/2 in a cell, right? आइए, अभी भी नहीं समझ में आया तो रट लो, और कोई विकल्प नहीं. Can't waste so much time. Diamond cubic crystal structure. Here again it is a cubic crystal structure. So there would be 8 atoms at the corners. So first thing is there are 8 corner atoms. There are 8 corner atoms, one at each corner. There are 8 corner atoms, there are 8 corner atoms, one at each corner, right. There are 6 face atoms. There are 6 face atoms, one at the center of each face. Along with this, there are 4 atoms inside the cell. They are entirely within the cell, and they are situated at tetrahedral position. Tetrahedral position means they are bonding like this. 109.5 degree angle is there. So you can see like this, one atom is here, one here, one here, one here, and one more like this. So this is the geometry followed by them in 3D. So coordination number will be 4, because here you see, if I take this atom as reference, then 1, 2, 3, 4. These are the only atoms which would be touching to this. Why this coordination number is reduced? That is reduced because of the bond angle. Now the bond angle is 109.5 degree. It is a directional bond. So because of this bond angle, atom can be either at this or at this or at this. In between this region there cannot be any atom. So coordination number cannot be here 12. Instead it becomes 4. So this only thing which I am interested to tell you. So next is there are 4 atoms inside the cube at tetrahedral position. Tetrahedral position means they are making a bond angle of 109.5 degree with each other at tetrahedral position. So So if you calculate the effective number of atoms, then it will be equal to corner atom 1 by 8 into 8 plus face atom 1 by 2 into 6 plus 4 atoms inside the cube. Inside the cube means entirely they are contributing into the same cell. So n is equal to how much? 3 plus 1 4 plus 4 8 atoms per unit cell. This is the effective number of atoms. Although there are 14 atoms, 8 6 14 plus 4 18 atoms in making this cell, but out of these 18 atoms effectively there are 8 atoms per unit cell, because corner atoms are in the 8 identical cells, face atoms are in the 6 identical cells, like that. Now if you calculate, I am giving directly the value, not calculating APF for this. So APF is equal to 0.34. Those who are interested in calculation, they can refer the theory book. I have given it over there. Here not interested to calculate it. And coordination number is 4. These are the two important parameters. I am wanting to discuss this value. This is very important. Till now we have studied APF as 52%, 68%, 74%. You see FCC, that is 74% heavily packed. Only 26% volume is void in a cell. But here you see in diamond cubic 34% packing efficiency. 66% volume is void. Why this low packing efficiency? Although carbon atoms are very small in size and small atoms can be packed very closely, but here carbon atoms are not packed closely. Lots of volume of a cell is void. Why? What is the reason? So the main reason for this to become void is this bond angle. There is 109.5 degree bond angle, and because of this bond angle, because of the directional nature of bond, we are not able to utilize effectively the volume of the unit cell. This I told you during covalent bonding. Covalent bonds are directional bonds, and if a bond is directional bond, then atoms cannot be forming bond in all the directions. They would be at certain direction, then only the bond would be formed, and hence volume cannot be utilized effectively. So it will have very low packing efficiency. So diamond has very low packing efficiency. This is the only important thing from this diamond cubic crystal structure. For detail, you can refer theory book that is available to you. Please write down these things. Quickly write it. Milu, it's not same as zinc blend structure. Zinc blend is different structure that we would be studying in future chapter, that is known as ceramic. There I would be telling you. Although it is matching with that structure, more or less they look like same, but they have internal difference that we would be discussing when I would be teaching you ceramics. Shall we go ahead? Right. नहीं बेटा, weight is different thing. Atomic packing factor is different thing, right? Omkar Sahu, weight and packing efficiency both are not same. Shall we go ahead? Next is hexagonal closed pack structure. Briefly we want to study, not in depth, hexagonal closed pack structure. It is popularly known as SCP. This kind of structure is observed in magnesium, Mg, zinc, cadmium, etc. Here there are 6 atoms at the top corner and there are 6 atoms at the bottom corner. So there are 12 corner atoms. Top corner 6 and bottom corner 6. Top 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now you see, to make a hexagon, one angle should be 120 degree. So this angle is your 120 degree. If there is 120 degree angle, then any corner atom can contribute in 1, 2, 3. 3 cell from front and 3 from back. So it will be contributing in only 6 cell. Any corner atom now is able to contribute only in 6 cell. So its contribution in a particular cell cannot be greater than 1 by 6. So its contribution is 1 by 6. Whereas in case of cube it was able to participate in 8 cells. That's why the contribution is 1 by 8. Here each corner atom is contributing, each corner atom is participating in 6 identical cells. Hence its contribution in a cell, is 1 upon 6. First thing, there is one atom at the center of each face. So one atom at the center of top face and one atom at the center of bottom face. Face atoms still contribute 1 by 2. This is the top face, then it would be the bottom face of the upper cell. इसके ऊपर भी एक cell होगी and it would be the bottom face of that cell. So it is effectively in 2 cells and hence its contribution in a particular cell is 1. There are 3 atoms inside the cell. They are located not here, they are inside. So you can represent like this. Representing in this diagram is little bit difficult, but still I will try. So here one atom is here, one atom is here, one you suppose back side, and they are equal distance from this face atom. Means all these 3 are touching to the face atoms. They would be touching to this, they would be touching to this face also. Means these atoms are at equal distance from top face and bottom face. This condition will be satisfied only if we know that to make hexagon 2 dimensions should be same. So same dimensions I am assuming A, but the larger dimension should be equal to C. मान लेते हैं, ठीक, A is equal to B but does not equal to C. So C by A ratio means larger dimension upon smaller dimension ratio should be 1.63. Then only this structure will be formed, otherwise it is not possible to make this structure. ये question पूछ लिया जाता है कई बार. Now if I calculate effective number of atoms, so 1 by 6 for each corner atom. How many corner atoms are there? 6 top, 6 bottom. So there are 12 corner atoms plus 1 by 2 into face. How many face atoms are there? 1 top face, 1 bottom face, 2 plus 3 atoms are inside, these 3 which are inside. So we have effectively N is equal to 2 plus 1, 3 plus 3, 6 atoms per unit cell. 6 atoms per unit cell. This is the value of N. Coordination number is very simple to calculate. Although if you cannot calculate, then you have to keep in mind. I will tell you trick how can you keep in mind. This atom, if you take reference, these 6 corner atoms would be touching and these 3 atoms are touching. So 6, 3, 9, and similarly 3 atoms would be here, they would be touching it above this, like this face atom is touching to this. So 6 within this, 3 this and 3 this, 12. So coordination number is 12. Cn is 12. FCC I am directly writing, APF I am directly writing, that is 0.74. The best way to keep in mind these things is same as FCC, same as FCC. These two data is same as FCC. So this is all about hexagonal closed pack structure. इतना ही आपको इसके बारे में जानना है. Please note it down. Yes, Manoj. Effective number of atom is high. It means volume is increasing because of directional nature. So that is taking more atoms, but atomic packing efficiency is low. It means atoms are not able to utilize efficiently the given volume. Next, we would be studying interpenetration of FCC when we would be studying the crystal structure of ionic solids, and that would be taught in the chapter named as ceramic material. But as name is suggest, when two FCC structures penetrate each other, that will be known as interpenetrating FCC. Noted? Okay, let us go ahead. If we know the crystal structure, we can comment on the several properties of the materials. So one of the very important properties is density of the material. Density of the material can be calculated if we have idea about the crystal structure. How? Let us see. So let's put heading density calculation. Density calculations. Let us suppose we define as N is equal to N by Vc, where N is number of atoms per unit volume, number of atoms per unit volume, per unit volume. N is effective number of atoms, effective number of atoms per unit cell, per unit cell, and Vc is volume of unit cell, volume of unit cell. This would be given as Na rho upon A, where rho is density, A is atomic weight, atomic weight, and Na is Avogadro's number, Avogadro's number. Na is 6.023 into 10 to the power 23 atoms per mole. This is Avogadro's number. Now, you please see. From this we have rho, and rho is equal to N into A upon Na into Vc. This is density. This way you can calculate density. So, if volume of the unit cell is known, that can be known only if you know the type of the unit cell, then you can calculate the volume of the unit cell, and with the help of that you can calculate this. So, let us see. First you do this, then we would be doing one numerical problem on this. Today I tried to, although I am speaking in English, but I have tried to make the words very simple. So, hopefully those who are trying to and also trying to speak little bit slow. So, those who will be trying to understand, they will definitely understand the things which I want to tell you. Those who are not wanting, for them I am not interested, because you did your effort, I did my effort, and there was different communication. For you the communication was different, for me the communication was different. So, we could not reach to the common minimum program. Shall I go for the numerical problem? Yes, let us do a numerical question. Copper has an atomic radius. Do a question. Copper has an atomic radius of 0.128 nanometer. Copper has an atomic radius of 0.128 nanometer and an atomic weight of 63.5 gram per mole. Atomic weight of 63.5 gram per mole. Calculate the density of copper. Calculate the density of copper. calculate the density of copper. You need to calculate the density of copper. Please do it. Na is Avogadro number. For this Achilles, you have to refer Avogadro's law. Although Avogadro has given that law for gases, but later on it was modified for the solids and liquids as well. Avogadro says that at constant temperature and pressure, equal volumes of two gases will have same number of atoms. So from there he related basically volume and number of atoms. There we got a proportionality constant, and that constant is known as Avogadro number. So this is coming from that Avogadro's law. So Mr. Avogadro proposed that at constant temperature and pressure, equal volumes of two gases will contain equal number of atoms. And that first this law was made for the gases, and later on it was modified for solids and liquids as well. So the law for the solid has been written in front of you. Physics ना एक इंजीनियर का पीछा कभी नहीं छोड़ेगी. So you cannot ignore physics. Whenever you are wanting to learn anything in science, you have to learn physics. Anyone did this? Pratik. That is the question, Pratik. Which type of packing we should adopt? That is the question to solve this problem. If you are able to figure it out, then you will be easily solving this problem. Humaira Afrin. बहुत अच्छा Humaira. You did it very well. Which branch you belong? Your answer is 100% correct. Let us see. First of all, see the material. This is copper. Copper is FCC. This must be known to you. And that is why in each group I has given some examples. So these are the examples which I have collected from several examinations over the period of time. So these are the important examples, and that you have to memorize. So in FCC I have given you several examples. Out of those several examples, one is copper. You see here. Silver, gold, platinum, nickel, copper, aluminum, lead. So copper is what? FCC. It is FCC. Let us go for it. So if copper is FCC, then effective number of atoms, N is how much? 4 atoms in a unit cell, right? And volume of unit cell. This density we are wanting to calculate in gram per centimeter cube. ये मैं लिखना भूल गया. Actually I have not given you options, and all the options were in gram per centimeter cube. N is 4 atoms. Vc is volume of unit cell. Volume of unit cell. FCC is cube. So volume of cube is what? A cube. But A is not known to us. Don't worry. For FCC, you know the relationship A and R. A is 2 root 2 R. Put this value. So we have 2 root 2 R cube. So from this volume of FCC unit cell, Vc is 16 root 2 R cube. In engineering services 2017, they ask what is the volume of FCC unit cell. So the volume of FCC unit cell is given by 16 root 2 R cube. R is available to us. R is how much? R is 0.128 nanometer. But we are wanting in centimeters, so it will convert as 0.1 128 into 10 to the power minus 7 centimeter. 1 nanometer is 10 raised power minus 9 and 1 centimeter is 10 raised power minus 2, right. Let's go for it. Now if I put all these values, then we have rho. What we have determined for the rho? We want to calculate rho. Rho is Na into Avogadro number n into A upon Na into Vc. Put all these values with units. Rho is 4 atoms. Na is 63.5 gram per mole. Sorry, A is. Na is 6.023 into 10 to the power 23 atoms per mole, and this should be multiplied by Vc 16 root 2 r cube, and r is 0.128 10 to the power minus 7 cube. This is centimeter cube. You simplify all these things, mole will get cancelled, atoms will cancel, you will get gram per centimeter cube. On solving it, it comes out as, rho is coming out as 8.89 gram per centimeter cube. This would be the answer for the density of copper. Someone please write down it. This way we are going to calculate such questions. Please do it. Yes, 8.89 gram per cc. हिमेश जी कहाँ 10 to the power 14 निकाल डाला? Along with this subject, which subject is running parallelly? For EC students, which subject is running? For each branch I want to know. For EC, which subject? For electrical, for mechanical, for civil. But since in this batch there are lots of batches are merged, so maybe different subject in different branches. Arpit, the value of Avogadro number should be memorized. They may not give it because it is considered to be the universal constant. For civil, survey is going good. For mechanical, SOM and industrial, okay. Civil, irrigation also going on. So different batches, different surveying. अच्छा, वॉल्यूम का क्यूब नहीं लिखा मैंने. अच्छा, आप भूल गए थे करना. ठीक है, वही लिखा तो मैंने. Advanced electronics for EC, communication and measurement for EE. Advanced electronics and communication for EC. For electrical it is communication. Strength of material for mechanical. Good. So for RCC for civil. Now you can see how many of you are in this from different batches. In a branch civil, someone has written RCC, for someone survey, someone other subjects. In electrical, measurement is running, power electronics is running, so many subjects are running. In EC, advanced electronics, communication, all that. Actually, that was the biggest problem because of which all these nuances happened, and there are so many batches in this particular class, and everyone was expecting that he is doing only class. Ankita beta, ये decimal and all these things has to be kept very carefully. The calculation errors are very common in exam, so you try to practice before the examination to avoid the calculation errors, because calculation errors are one of the killing factors for the low score, and they become a reason for the negative marking. राजांशु इज राइटिंग, सर अपना कुछ नहीं चल रहा फ्रॉम मैकेनिकल बैच 10 जून अजैन। अरे आपका तो सब खत्म हो गया होगा, आप तो चिल मारो। मनदीप इज राइटिंग 9 AM to 10 PM क्लासेस चल रही। अब लेट एडमिशन लोगे बेटा तो ये दिक्कत तो होगी ही होगी। आइंस्टीन बाबा हैज गिवन अ वेरी गुड रूल कि energy can neither be created nor destroyed. It can be only transformed from one form to another form. So to perform a particular job, certain amount of energy is compulsorily required. You have to generate that energy. किसी न किसी तरीके से, कहीं ना कहीं से आपको वो एनर्जी लेके आनी पड़ेगी, कोई विकल्प नहीं है उस एनर्जी का। So to crack a competitive examination, certain threshold level of energy is required. Those who took admission in the early stage, they put that required amount of energy slowly to crack the exam. But those who took admission in the later on stages, very late they took admission in June, July. So if time is limited, so to reach up to the threshold level of the required energy, they have to put more effort. So in this process you should not feel pity on yourself. इस process के दौरान आपको अपने ऊपर दया नहीं लगनी चाहिए, अपने ऊपर गुस्सा नहीं आना चाहिए. You should not feel bad for anyone else also. आपको इंस्टीट्यूट पे भी गुस्सा नहीं होना चाहिए. ये तो बड़ी अच्छी बात है कि कोई इंस्टीट्यूट पैसा ले करके ज़बरदस्ती पढ़ा रहा है, अदरवाइज तो लोग पैसा लेके नहीं पढ़ाते हैं. सो इट्स गुड समवन इज कॉलिंग यू टू टीच मॉर्निंग टू इवनिंग, इसमें तो वो अपना काम तो कर ही रहे हैं. बट द पॉइंट इज कि आपको लगेगा कि एज अ स्टूडेंट हाउ कैन आई मैनेज द शेड्यूल. आई विल सजेस्ट यू कि stop thinking about the result. Stop thinking about the result and start thinking कि how much syllabus you can cover beautifully before the examination. The day you will start covering the subject without thinking the examination, and if you are become to able to cover even 60 to 70% syllabus beautifully, your chances of getting selection, performing well in the examination will be very high. Most of the people could not crack exam because they come under pressure in the last stage of the examination, and they come under pressure because they started feeling that very less time is left and the syllabus is not covered. Because of this they stop studying. They just keep on thinking and go enter into the negative loop and waste their all energy in thinking process only. The best way to come out of it is कि if I have read one subject and there are 10 questions from that subject, now I will give my best to attempt 8-9 questions from that subject. यदि इस तरह की थिंकिंग आप बना लोगे, सोचने का अपना तरीका चेंज कर लोगे, सो बहुत ज़्यादा चांसेस हैं कि आप एग्ज़ाम के करीब पहुंच जाओगे या एग्ज़ाम क्वालिफाई कर लोगे. यू कैन नॉट स्ट्रेच टाइम, यू कैन नॉट डिले एग्ज़ाम, यू कैन नॉट कंप्रेस सिलेबस. व्हाई आई एम टेलिंग ऑल दीज थिंग्स कि दीज ऑल फैक्टर्स आर बियॉन्ड द कैपेसिटी ऑफ योर कंट्रोल. You can do only one thing, you can study as much as possible. So the only factor which is in your control is to study, and to study positively. Remaining all other factors are out of control. So study positively. तुलसीदास जी हिंदी के एक बड़े अच्छे पोएट हुए हैं. उन्होंने एक बुक लिखी है रामचरितमानस. उन्होंने भक्ति के एंगल से लिखी है, बट दैट इज मेटाफिजिक्स. The book has several concepts which are beyond the physics, and they talk about the energy, they talk about several other things. So there he has written one beautiful line, that is, सकल पदार्थ अहें जग माही, कर्म हीन नर पावत नाही. In this world, everything is available, but those who are not working hard, they don't get it. It means what? Those who will work hard, they will definitely get it. तो अब ये प्रश्न उठता है कि भाई कैसे, काम तो सब करते हैं, तो कैसे किसी को सब कुछ मिल जाता है, किसी को नहीं मिलता है? How will you define कि who is working hard in the right direction, who is working hard in the wrong direction? So for this he has given another beautiful line in the same book. जाकी रही भावना जैसी, प्रभु मूरत तिन देखी तैसी. The way you think, the same way things are presented before you. जिस तरह से तुम सोचते हो, तुम्हारे सामने उसी तरह की चीजें घटित होने लगती हैं, उसी तरह की चीजें तुम्हें दिखाई देने लगती हैं. It means anything which is coming in your life, that is just a reflection of your thinking process. जाकी रही भावना जैसी, भावना मीन्स थिंकिंग, प्रभु मूरत तिन देखी तैसी. उसने उसी तरह से सामने भगवान को देखा. It means he is wanting to say कि anything in your life, whether it is success or it is failure, it is material word success or it is something else, anything which is happening in your life, it has not come into the sudden way. It is coming because of your thinking. So जैसा आप सोचोगे उसी तरह से आपके जीवन में चीजें होंगी, उसके अलावा कुछ अलग नहीं हो सकता है. I am telling you this story. The reason behind this, to get good things in life, to become successful in life, पढ़ाई वढ़ाई ये वो सब चीजें बाद की बात है. The first thing is कि अपनी भावना चेंज करो, अपनी थिंकिंग प्रोसेस चेंज करो. स्टार्ट थिंकिंग इन द पॉजिटिव मैनर. जब आप क्वांटम फिजिक्स पढ़ेंगे, आई एम अ स्टूडेंट ऑफ क्वांटम फिजिक्स, basically belong from electronics engineering. I have to teach electronics and communication, so there lots of concepts of quantum physics are utilized. So quantum physics says that ki the purest form of energy, that is energy, is in the form of wave. So when we think, that is basically energy in the form of wave in our mind. And Einstein says that energy can neither be created nor destroyed. So this energy which has generated, it will impact the surrounding. जिस भी surrounding में है energy, उस surrounding को impact करेगी. If any energy has generated, it is going to impact, because it cannot be destroyed. So that energy is going to be transformed, and that will be transformed with the help of surrounding, with the help of medium. So if some energy is generated in your brain, so the medium is your life, you. So this energy is going to transform your life. Definitely, no one can deny it. It is going to transform your life. बट एनर्जी का खेल बड़ा निराला है. इफ एनर्जी इज गिवन टू अ पॉजिटिव पर्सन, he will use it and will generate electricity and will lighten up the whole city. एनर्जी किसी पॉजिटिव व्यक्ति को दी जाएगी तो वो उससे बिजली बनाएगा और बिजली बना करके पूरे शहर को जगमगा देगा. बट इफ द एनर्जी इज गिवन टू एनी टेररिस्ट, the energy is given to any negative person, तो वो उससे बम बनाएगा और बम बना करके उसी शहर को उड़ा देगा. It is the same atomic energy which can enlighten your city and which can destroy your city. Same happens in life also. The energy which has developed in your mind, if it is developed with a positive attitude, it is going to enlighten your city of life. But if it is developed with negative attitude, with terrorist mind frame, then it is going to destroy your city of life. So be positive, do your best. Life is not about 2 months, 3 months, 2 exam, 1 exam. It's a very long journey. So in that long journey, if you will develop positivity, a way of thinking in the positive manner, then you are going to get something better, something bigger in your life. Let's come back to the topic. So now coming back to the topic, next topic is Miller indices for the directions. Miller indices for the directions. Indices for directions. Although it is not very important, it is part of the syllabus, so I am teaching it. It has never been asked, but still we have to cover. So many of you have written several things, but I will be reading it later. Yes, Ruchi, all prime batches has been merged here. What is direction? Any vector which is joining 2 points in the crystal, two atoms in the crystal, that will be known as direction. So basically it is nothing but a line. So first of all, try to crystallographic direction. A crystallographic direction is defined as a line between 2 points. A crystallographic direction is defined as a line between 2 points. Between 2 points. A crystallographic direction is defined as a line between 2 points. Actually, we have seen that most of the materials are anisotropic in true sense, although we assume them isotropic, but they are anisotropic. So in anisotropic materials, properties will differ from direction to direction. So Miller indices are basically a technique to give name to these directions. इसका और कोई physical significance नहीं है. It has only physical significance कि this is a technique to name the directions, numerically to represent the directions. जैसे मेरा नाम सुनील है. What is the logic behind? The only logic behind this name is that there are 130 crore people in this country, so I should be given certain name so that out of these 130 crore people can identify me regarding whom they are talking. So similarly here there are n number of directions, so we would be giving certain nomenclature to the directions. That is the purpose of Miller index. So to give name to these directions, we need to follow certain steps. So I am taking an example, and with the help of that example, I will be trying to explain how we can calculate the direction. So let us take an example. Let us suppose we have this cell. This may be cubic or it may not be cubic. That doesn't matter for us. Suppose I am wanting to calculate, here atoms are located at each corner, let us assume this, atoms are located at each corner, suppose. I am taking it as simple cubic crystal structure. Now suppose we are wanting to calculate Miller indices for this direction which I am showing. We want to calculate Miller index for this direction. So what are the steps which we need to follow? Step 1. Select a coordinate system. Such that origin lies on the given line, Select a coordinate system such that origin lies on the given line. So let us select it. This is origin O. I am taking this line as A. So now you see the coordinate system can be defined like this. This is our coordinate system. Any of these three axes can be assumed at, let us suppose this is x, this is y, this is z. You can take it x, y, z, किसी को भी ले सकते हैं. So this is the coordinate system we have defined. So O, x, y, z. This is the coordinate system. Now step 2. Go for the step 2. Determine the coordinates of another point on the line. Determine the coordinates of another point on the line. Another point on the line in terms of lattice parameter. In terms of lattice parameters, that is unit cell dimensions. Lattice parameter means unit cell dimensions. You see, my dear friend, let us suppose it is xy axis. So this is y and this is x. This is your line A and O. This line is cutting x axis here. This point is what? A. And it is cutting here. This point is what? B. So this and this is not going into the z direction. So this is entirely in x and y plane. So the coordinates of this point A can be written as A, comma B, comma 0. You can write like this. B is unit cell dimension along y axis. This is B, and A is unit cell dimension along x axis. It is only in xy plane, so 0 will be the value for the z axis. So we are having coordinates of another point A on the line. He may give you also, he may give you A by 2, B by 3 like that some other point. So you would be writing that if it is given A, B, 0 into C I can write, because 0 multiplied by something will remain 0. So it is coordinates of another point in terms of unit cell dimension ABC, where ABC are unit cell dimensions. Step 3. Step 3. Discard ABC, discard AB, A, B, C and consider only multiples of ABC. Consider only multiples of ABC. multiples of A, B, C. What is the multiple of A? This is 1 into A, so it is 1. What is the multiple of B? B 1 into. What is the multiple of C? 0. Now step 4. These are already integers, but suppose you have been given any point and they are not integers. Suppose you have been given A by 2, B by 3 and 0. So it is 1 by 2, 1 by 3 and 0. So if it is in fraction, convert it into smallest integer. How can you convert? Multiply it by 6, that is the LCM of 2, 3. So it will become 3, 2, 0. You will get the smallest integer. So that I am wanting to tell you, okay, convert multiples into smallest set of integers, smallest set of integers if required. In this case it is not required, they are already smallest integers, so we need not to convert them. So convert multiples into smallest set of integers and put them into square bracket इसे स्क्वायर ब्रैकेट में पुट कर दीजिए. So it will come out 1, 1 and 0. This is the Miller indices for direction OA. Put them into square bracket without commas. Comma नहीं लगाते हैं, that is convention. So without commas, this 1, 1, 0 is Miller indices for direction OA. Miller indices for direction OA. This way you need to proceed. These are the steps which need to be followed to determine the direction OA. Miller indices for direction OA. Similarly, you can calculate for any other direction. These are the steps you need to follow. Please note down it. Lattice Muhammad Sajid I have explained in last class. Please revisit your notes again. Lattice means three-dimensional periodic arrangement of points in space. Please refer that. Yesterday's class. Do it quickly. थोड़ा जल्दी करें. We have to finish this chapter today. Today's target is to complete this chapter. Those of you may require any kind of information related with competitive examinations or any kind of the things you feel is going out of control, you can contact me, you can talk to me. And those who are my students in other subjects, they know my behavior. In this batch, actually I am not the natural person which I used to be. The reason is very different, you know that very well, but still it should not affect your preparation. So if you are feeling any kind of difficulty, you can contact me, you can discuss, and I will try to rectify it. I will try to give you the best solution for that particular thing. Next, let us suppose we have this crystal system. Let us suppose we have this crystal system. This is the crystal system we are having. So, this I am assuming that there are atoms at each corner. So, we have corner atoms like this. You can take any other crystal system also, you can take FCC, you can take BCC, any one. The procedure will remain same, that is not going to be affected. Now, suppose I want to determine this direction's Miller indices. So, I will be taking origin at this point and will be trying to calculate for this. So, suppose this is x axis, let us suppose, then y, z and like this. So, we would be getting 1 0 0, right. Now, let us suppose I have to calculate for this line O dash A dash, I am assuming. I will take origin as this point and then x axis at this, y at this and z at this. Again I would be getting 1 0 0. Since we have freedom to select the origin, hence any corner atom of the unit cell we can take at origin point and we can define the crystal coordinate system. So, we can take this point as origin to calculate the Miller indices for this line. Similarly, we can take this point as origin to calculate the Miller indices of this line. And in both of cases, we are getting the same value for Miller indices. Both of these lines are parallel to each other. Hence, we can conclude that parallel lines are having the same Miller indices in the crystal. This I wanted to tell you with this example. All the parallel lines will have same value of Miller indices, as here OA and O dash A dash both are having 1 0 0. So, please note down this very important point. All the parallel directions have same Miller indices. All the parallel directions, all the parallel directions have same Miller indices. All the parallel directions have same Miller indices. Please note it down. Yes, they will give you direction and they will ask calculate the Miller indices. Although as I told you for direction they have never asked till now, but still we need to study it, they may ask. I told you Miller indices is nothing but a way to represent the direction in numerical terms. So, it is basically a method to name the directions where you have to follow the certain steps. Yes, Giri, I told Miller indices is a way to name the directions. We need to follow certain set of rules and hence we would be getting the nomenclature for each direction. Is it done? Shall we go ahead? I am saying that if in step 4, if you get the values which are not integer, like 1 by 2, 1 by 3, 0, like this. So convert them into smallest integer. How can you convert them? Multiply them with the common factor. That common factor can be the LCM of denominators. Like suppose you have 1 by 2, 1 by 3 and 0, then the LCM is 2, 3, 6. And if it is LCM of 2, 3 is 6. So if you multiply by 6, it will become 320. So Miller indices will be 320. Although for the given problem we need not to require to convert it, because already it is in the smallest integer. हर्षित we can get it. 3D directions भी होती हैं, so we can get it. Where you have coordinates of 3D, vector algebra पढ़ा होगा, so we can have 3D direction. 3D geometry में जाइए, you can get it. Next, Miller indices for the planes. Miller indices for the planes. This is important. This they generally ask. Direction just I taught for the sake of completeness, but this they ask. Let us suppose this is a crystal. Suppose you have a crystal. This is the unit cell, and let us suppose atoms are only at the corners. You can take any kind of cell. I am taking corners only, just for the explanation purpose. Now suppose they ask you the Miller indices for any plane. Let us suppose I am giving you this plane and they are asking Miller indices for this plane. Any plane they may ask. Let us suppose they are asking Miller indices for this plane. So you have to find out Miller indices for this plane. Miller indices for this plane. How can you calculate? Step 1. Select a crystal coordinate system. Crystal coordinate system. Select a crystal coordinate system such that origin is not lying on the plane, such that origin is not lying on the plane. Select a crystal coordinate system such that origin is not lying on the plane. So I am selecting, let us suppose this is our front plane, so I am selecting origin at the back plane, and hence we have a coordinate system like this. Let us suppose this is x axis, this is y axis, and this is z axis. So O, x, y, z, this is our coordinate system. O, x, y, z. O is not lying on the plane. We are talking about front plane, and I am assuming O is at the back plane. Dotted lines. Next, step 2. Determine the intercept made by plane on each axis. Determine the intercepts made by plane on each axis in terms of unit cell edge lengths, in terms of unit cell edge lengths. You see, x-axis it is cutting at point A. So, coordinates at x-axis is how much? This point. This is A. Y-axis it is B. Z-axis it is C. So, intercept in this case is ABC. A, B, C. This can be written as 1 into A, 1 into B, 1 into C. These are the intercept made by the given plane on each axis. Step 3. Drop ABC, and consider multiples of ABC. Consider multiples of A, B and C. Multiple of A is 1, multiple of B is 1, multiple of C is 1. It can be anything also. Let us suppose it can be 2A, 3B, 4C. Intercept. He may give you these are the intercepts. Then the multiples will be 2, 3, 4. This can be the multiples, right? So, he may give you what are the various intercepts made by the plane. Next step is very much different than the line. In the line, in this step we convert into multiples, into integer, but for the plane we have to perform one more step, that is get reciprocals of multiples. Get reciprocals of multiples. In this case it does not matter, like reciprocal of 1 is 1 by 1, 1 by 1, 1 by 1. So, it is nothing but again 1, 1, 1. But suppose these are the numbers, then matter. If it is 2, then reciprocal will become 1 by 2. If it is 3, then it is 1 by 3. And if it is 4, then it is 1 by 4. So, get the reciprocal of multiples. This I am telling you some example, some other example that may be the case. Now, step 5. Step 5. Reduce reciprocals into smallest set of integers. Reduce reciprocals into smallest set of integers. Smallest set of integers. And put them into a small bracket. Put them into small bracket without commas. Put them into small bracket without commas. यहाँ तो already integer है, so we need not to worry about this. Put them into a small bracket 1, 1, 1, and this will be the Miller indices for given plane. But this will not be case always. Suppose you have reciprocals like this. So, if reciprocals are 1 by 2, 1 by 3, 1 by 4, how can convert into a small integer? 2, 3, 4 LCM, that is 12. So, multiply by 12, it will become 6. It is 4 and it is 3. Put them into a small bracket without comma. This will be the Miller indices. So, Miller indices के लिए what are the steps you need to follow? The first step is कि select a crystal coordinate system such that origin is not lying on the plane. जबकि line के case में origin must be on the plane, but here origin should not lie on the plane. Then step 2, determine the intercepts made by plane on each axis in terms of unit cell edge length, and then drop ABC and consider multiples of ABC. Get reciprocals of the multiples. Reduce reciprocals into a smallest set of integers and put them into a small bracket without commas. This will give you the Miller indices. This is the standard procedure you have to follow. Please do it quickly. Samriddhi, directions be defined. So, if you change the x, y, z coordinates axis, then accordingly Miller indices will also change. Do it quickly. Right. Now, suppose please do it quickly. Achilles, keep patience, everything has some use, then only the things are studied. Without use, nothing has been studied in the science. So, everything has some use. All right, come back. Let us do a question. Suppose you have a crystal like this. You have a crystal like this. First of all, we are wanting to note one point, then we will be doing question like this. Let us suppose I want to calculate the Miller indices of the front plane. Then I would be taking origin at the back side, and suppose if this is x axis, this is y, this is z, then the value would be 1 0 0. Similarly, if we want to calculate Miller indices for the back plane, then I would be taking origin at the front side, and again we would be getting the same value. What I am wanting to tell you, like the directions we have same Miller indices for the parallel direction, similarly for the planes also we will have same Miller indices if they are parallel, because we have freedom to choose the origin. So, if I am talking about front plane, I will take origin at the back side and do the calculations. If I am talking about back plane, I will be taking origin at the front side and will be getting the same value of the Miller indices. So, this way both of the parallel planes will have same value of Miller indices. So, you note it down. Note, parallel planes are having, all parallel planes have the same Miller indices. All parallel planes have same Miller indices. All parallel planes have same Miller indices. All parallel planes have same Miller indices. प्रतीक कह रहे हैं कि अगर स्क्वायर रूट आया तो क्या करेंगे, स्क्वायर रूट आया तो उसको भी इंटीजर में कन्वर्ट करो, स्क्वायर रूट को फ्रैक्शन में कन्वर्ट करो, फ्रैक्शन को आप फिर से न्यूमरेटर एंड डिनोमिनेटर के टर्म में कन्वर्ट करो, न्यूमरेटर और डिनोमिनेटर में कन्वर्ट करके उसका एलसीएम ले करके एंड देन कन्वर्ट करो। यू डोंट नो द बेसिक मैथमेटिक्स, डू इट। नहीं आएगा, तुम्हारी इमेजिनेशन के हिसाब से क्वेश्चन नहीं आते। Shall we go ahead? Right. Please do one question. With the help of that question, I would like to explain few things. Determine Miller indices. Determine Miller indices. Miller indices for the plane. For the plane. प्लेन दिखा रहा हूं आपको कौन सा है। दिस इज सपोज क्यूबिक यूनिट सेल। दिस इज क्यूबिक यूनिट सेल। Right? Now suppose in the question he is giving you axis. This is origin and he is giving you axis like this. In the question itself he has given you axis. So अब आपके पास फ्रीडम नहीं, ठीक, मतलब फ्रीडम तो है ही लेकिन उसने दे रखा है, राइट, एक्स वाई जेड, दीज आर द कोऑर्डिनेट्स ही हैज गिवन टू यू। नाउ आई सेइंग दैट लेट्स नेम दीज ऑल ए बी सी डी ई एफ जी, right? So he is defining a plane and that plane is O to F and then it is F to C and then it is C to B and then it is this O to B. O to B. ठीक है। Now this plane OBCF, OBCF, इसके लिए आपको मिलर इंडाइसेस पता करना है। प्लीज ड्रा इट क्विकली। डिटरमाइन मिलर इंडाइसेस फॉर द प्लेन OBCF। Done? यहाँ एक प्रॉब्लम है। द प्लेन इज, योर प्लेन इज OBCF. According to Miller indices method, origin should not lie on the plane, but here origin is lying on the plane. Origin O is lying on the plane, lying on the plane. Origin is lying on the plane. If origin lies on the plane, then we need to shift origin. We need to shift origin and define new coordinate system and define new coordinate system. Define new coordinate system. We need to shift to origin and define new coordinate system. Now please shift the origin and define new coordinate system. We can define new coordinate system like this. This O can be shifted either at this side or at this side or at this side or at this side. If we go this side, then it will again be on the plane. So we don't want origin to be on the plane. So this side we cannot go. But we can go this side or this side, any side at unit distance. कोई फर्क नहीं पड़ेगा. Any corner of the unit cell can be taken as origin. So for an example, let us suppose I am taking this corner as origin. You can have multiple answers for this question. Out of the multiple possibilities, only one will be given in the option, right? So let us suppose this point be considered at origin, new origin, and defining axis like this. This is x dash, this is y dash, and this is z dash. Now new coordinate system is O dash, x dash, y dash, and z dash. Here origin does not lie on the plane. Determine the intercepts made by plane with respect to new origin. So intercepts. What are intercepts? Have a look intelligently. New x-axis is this, so intercept is this. This line is what? Edge length A, so it is A. New positive y-axis is this, but your intercept is along negative axis. And how much distance? By the unit cell dimension. So it is minus B, right? Your origin is this, positive is this side and minus is this side. So it is along the negative y-axis, so minus B. In the z direction, it is not cutting anywhere. It is the z and this plane is not cutting. It means this plane and z direction are parallel to each other, and two parallel lines cut each other at infinity. This we assume. Though parallel line एक दूसरे से infinity पर मिल रहे हैं, this is the assumption we took, right? Infinity multiplied by something will remain that thing itself. So infinity into c will remain infinity. This is intercepts. Once you have get intercepts, then write only multiples. So multiples of ABC are what? A ka multiple 1, B ka multiple -1, and C ka multiple it is infinity. Then get the reciprocals of multiples. Let's write the reciprocals of multiples. 1 ka reciprocal is 1, -1 ka reciprocal is -1, and 1 by infinity. 1 by infinity is 0, so it is 0. And then reduce these multiples into smallest integer. They are already in integers, so put them into a small bracket, you will get Miller indices. So Miller indices are 1, 1 and 0. This minus, for this minus you apply bar over the digit. Bar on any digit in Miller index represented that intercept is made along negative axis. If bar is on the first digit, means it is along negative x-axis. If it is on second digit, then it is negative y-axis. If it is on third digit, then negative z-axis. So bar represents that intercept is made along negative axis, intercept is made along negative axis. How will you get 0? You will get 0 only if this is infinity. So reciprocal of infinity is 0. There is no other way. But infinity will come when plane is parallel to the direction. So 0 is indicating that this plane is parallel to z direction. So if the first digit is 0, then plane is parallel to x direction. Second digit is 0, then plane is parallel to the y direction. And third digit is 0, then plane is parallel to the z direction. So you can write it here. 0 represents that. 0 represents that. Represents that the given plane is parallel to the corresponding axis, parallel to the corresponding axis. The given plane is parallel to the corresponding axis. Please note down this. ये सबसे डिफिकल्ट प्रॉब्लम हो सकती है, इस पे कुछ कंसेप्ट भी समझाना था, दैट्स व्हाई आई टुक दिस. प्लीज कीप इट. तो 0 का रेसिप्रोकल लेना ही नहीं है अखिलेश, दैट्स व्हाई ओरिजिन नीड टू बी शिफ्टेड. Yes, Prateek. Quickly do it. Nishtha, in z axis there is no intercept made by the plane. No intercept means what? Plane is parallel to the z axis. So we assume that two parallel lines meet at the infinity. That's why I am writing intercept infinity. If you multiply infinity by any value, that will remain infinity. So I am multiplying infinity into c. That is nothing but infinity. C, because we want to calculate in terms of ABC. Achilles Gupta, yes, everyone's answer will vary, but out of the 4 options, only one option would be there among all the possibilities. So you have to reach to that possibility जो भी option दिया होगा. ऑब्जेक्टिव एग्जाम में लिखा रहता है कि दिए हुए ऑप्शंस में जो बेस्ट सुटेबल है वही चुने. तो मान लो यहाँ पर हम 4 तरह से ओरिजिन को शिफ्ट कर सकते हैं, तो 4 आंसर होंगे, लेकिन ऑप्शन में कोई 4 में से एक ही दिया रहेगा, तो तुम्हें वही एक ही चुन करके आंसर देना होगा, बाकी 3 तो ऑप्शन में ही नहीं होंगे. कॉमन सेंस. If it is conventional problem, then कोई प्रॉब्लम ही नहीं है. कहीं भी कर सकते हैं हम ओरिजिन. At any corner we can decide origin. सौरभ प्रशांत. Shall we go ahead? Right. Here we define one term, that is interplanar spacing. Interplanar spacing. It is defined as the distance between two parallel planes. It is defined as the distance between two parallel planes. For cubic crystal system, we are interested in only that. For cubic crystal system, this value is given as d. लेट अस सपोज प्लेन्स है हमारे एच के एल, उनके मिलर इंडाइसेस हैं. सो इट इज ए अपॉन अंडर रूट एच स्क्वायर प्लस के स्क्वायर प्लस एल स्क्वायर. हियर एच के एल is Miller indices of parallel plane. As we know that for all the parallel planes, Miller indices will be same. Miller indices of parallel planes. Parallel planes. Then A, unit cell edge length. Unit cell edge length. Unit cell edge length. Then DHKL. This is interplanar spacing. Interplanar spacing. Please do it quickly. Yes, HKL corresponds to the H is first digit is always x-axis, second is y and third is z, like 110, 120 like that, anything. Now we need to define few terms here. The first one is linear density. Linear density. Suppose we are wanting to calculate atomic density in a particular direction. So that density is known as linear density. It is defined as the number of atoms per unit length. It is defined as the number of atoms per unit length. It is defined as the number of atoms per unit length whose centers lie on the given crystallographic direction. It is defined as the number of atoms per unit length whose centers lie on the given crystallographic directions. Means LD is equal to number of atoms lying on the direction divided by length of the direction vector, length of the direction vector. Let me take an example to explain this. Suppose I take a FCC crystal structure. You can take any one, FCC, BCC, anything. Since FCC is very frequently asked in the exam, so I am taking FCC. Let us suppose you take an FCC crystal structure, and in that FCC crystal structure, you take an FCC crystal structure, and in the FCC crystal structure, let us suppose this is FCC, this is atom, this is atom, this is atom. Here I am taking an atom as a face, here an atom, here an atom, a face atom, an atom, an atom, an atom, an atom, an atom, an atom, this. Let us suppose in this direction I am wanting to calculate linear density. This we are wanting to calculate. Suppose मान लेते हैं this is the direction in which we are wanting to calculate along this. So I am taking this direction as O and A. Suppose we define crystal coordinate systems like this. We define the crystal coordinate system like this, x, y, z. Then what is OA? OA is, if you see, this is x axis 1, y is 1, so it is 1, 1, 0. This would be the OA. Right? So along OA, you are wanting to find out the linear density. Please make the front view. This is face atom. This is O atom. This is corner atom. This is corner atom. This is corner atom. Right? These are the atoms we are having. Now you see, my dear friend, if you connect these 2 points, so it is O, it is A, right? You have to find out linear density along OA. First of all, LD you want to calculate 1, 1, 0, this is OA. First of all, find out the length of vector, otherwise you will commit a mistake. So what is the length of vector? You are starting from this point and you are ending at this point. So R, 2R and R. So length of vector is R, 2R and R. On this length, how much atoms are centered? How much atoms are located? Center means located. If you take this whole atom, this is not located. Only half a portion of this atom is located on the line. If you are taking whole atom, then you have to consider this R also, but you are considering R only, this R. So it is 1 upon 2 for this atom. Similarly, 1 upon 2 for this atom, and this whole atom is on the line. So this way LD 1, 1, 0, this is nothing but 2 by 4R. 2 by 4R is 1 by 2R. One by 2R. R and A relationship is very well known for you. In the R and A relationship is very well known. FCC के लिए you can calculate it. So please note down this linear density. Yes, for all the parallel lines LD will be same. Next one is planar density. They may ask about planar density. It is defined number of atoms per unit area which are lying on a particular plane. It is defined as number of atoms per unit area which are lying on a plane, which are lying on a given plane. Let us suppose मैं यही plane consider कर लेता हूँ, this same जिसका मैंने front view बनाया. So if I consider this plane, this O, this atom, this atom, this atom and this atom. Let us consider this plane. So this plane is like this. Like this. We are wanting to calculate planar density for this plane. So PD, that is planar density, is number of atoms lying on the plane, divided by area of the plane, divided by area of the plane. So PD is equal to, now you see my dear friend, how much atom is located? This atom has only this much of the part, it is 1/4. This one is also only 1/4. This one again 1/4. This one again 1/4. And this whole atom. So 4 into 1/4 plus the mid one, that is whole atom, is lying on this plane, divided by area of the plane. So this dimension is A and this dimension is also A. So area is A into A. So this PD for this plane comes out as PD is equal to 2 upon A square. A and R relationship is well known for you for the FCC crystal structure. So you can put that relationship and calculate this value. Please do it for planar density quickly. अरे अखिलेश बेटा सेंटर्स लाई ऑन द प्लेन मतलब जो है उस प्लेन पर, जो नहीं है प्लेन पर उनकी बात ही नहीं करेंगे. दैट्स इट, दैट्स सिंपल. कि जो प्लेन पर हैं हम उन्हीं एटम्स की बात कर रहे हैं. वी आर टॉकिंग ओनली अबाउट दोज एटम्स व्हिच आर ऑन द प्लेन. वी हैव टू कैलकुलेट पर यूनिट लेंथ. सो पर यूनिट लेंथ कैसे निकाल सकते हैं? जब हमें प्लेन पर कितने, उस लेंथ में कितने एटम्स हैं ये पता चल जाए, देन ओनली वी कैन कैलकुलेट पर यूनिट लेंथ, अदरवाइज वी कैन नॉट. Shall we go ahead? Bragg's law of X-ray diffraction. Bragg's law of X-ray diffraction. बहुत डेप्थ में इसकी नहीं जाएंगे, एक लाइन में देखेंगे बस. Let us suppose these are the planes, parallel planes. Basically they will be having atoms on each plane. This line is normal to the plane. We have DHKL, that is interplanar spacing, we know it. This is interplanar spacing, DHKL. Suppose an X-ray is incident on this plane. This angle of incident is theta. Then it may be reflected like this, and this angle will also be theta. So if it is reflected from first plane, then I would be saying n is equal to 1. Suppose it comes like this and is reflected from the second plane, the same angle theta. So it is n is equal to 2. So here n is known as order of reflection, order of reflection. And DHKL is interplanar spacing, interplanar spacing. Theta is angle of incidence, angle of incidence, angle of incidence. And if lambda is wavelength of X-ray, wavelength of X-ray, then according to Bragg's law, n lambda is equal to 2d HKL sin theta. This equation is generally asked in the examination. You please write this. This is known as Bragg's law of X-ray diffraction. Bragg's law of X-ray diffraction. बेटा इतनी क्लियरिटी लेके अखिलेश क्या करोगे? इंटरप्लेनर स्पेसिंग मतलब दो प्लेन के बीच का स्पेस, कोई भी वैल्यू एच के एल की रख करके कैलकुलेट कर लो. देयर आर एन नंबर ऑफ क्वेश्चंस आई हैव गिवन इन द क्वेश्चन बैंक, जा करके सॉल्व कर लेना. ठीक है, इसमें क्या क्लियरिटी चाहिए आपको? Done? Next heading. Let us suppose this is the atomic arrangement. This is the atomic arrangement. It is perfect, regular and periodic. So if any crystal is having regular and periodic arrangement throughout the crystal, then it will be known as ideal crystal. But ideal things do not exist in reality. I can say that any crystal with perfectly regular and periodic arrangement of atoms, any crystal with perfect and regular, with perfectly regular perfectly regular and periodic arrangement of atoms is known as ideal crystal, right? But in real crystals there are certain problems. Let us suppose one atom is missing. One atom is not available at its lattice site. So we cannot say that it is non-crystalline material. We will be saying that it is a material with certain defect. But at this point periodic order is not followed. So there is a disturbance in periodicity. There is change in periodicity of atomic arrangement. There may be possibility some impurity is there at the interstitial site, or there may be possibility some other material atom is there substituting. So this impurity is also creating a defect. It is also creating an imperfection. Here the periodic order of atomic arrangement is not followed. So whenever there is change in order, a periodicity of atomic arrangement, then a crystal defect is formed. So whenever there is change in order or periodicity of atomic arrangement, then a crystal defect is formed. So next heading is crystal defects or imperfections. So next point here we will be writing whenever there is change in order or periodicity of atomic arrangement, then a crystal defect is formed. Whenever there is change in order or periodicity of atomic arrangement, then a crystal defect is formed. There can be several reasons for these defects. You increase the temperature. Because of that temperature, suppose any bond is broken. So if bond is broken, the atom will become free and it will be displaced from its position. So at that point there would be a vacancy, and that vacancy will be known as a defect. Suppose you add some impurity, that impurity is of a smaller size, so it will occupy an interstitial position, that is a defect. Suppose you add an impurity and that impurity is of comparable size, so that will substitute the parent atom and that will be forming a defect. So there are several reasons. Whenever an atom is leaving its lattice position, so that vacant lattice position will be known as a defect. It will definitely create a defect. So all the natural crystals are having certain amount of defect. Defect-free natural crystal is not possible. First of all these crystals, basically materials, are found in earth crust. So from earth crust they are extracted and then they are purified. There is no metallurgical process which can 100% purify any material. So there must be some impurity. And if there is an impurity, that impurity is nothing but the defect. Because wherever there is impurity, that will change the atomic order, that will change the periodicity, it means a defect is formed. Even the end surface atoms are not periodic. Here periodic arrangement may be there inside the material, but at the end surface there is no periodicity. So this end surface is known as free surface. So this free surface itself is a defect. This free surface itself is a defect. कहीं तो crystal end होगा and wherever this is getting an end, there the periodic order is not followed, and whenever there is periodic order is not followed, there would be defect. Sometimes we willingly introduce defect to change a particular property of the material, either to upgrade it or to degrade it. For example, we have alumina. Alumina is Al2O3. That is basically a gem, ruby. Suppose we are having ruby. Ruby is a stone. Basically, it is a gem stone, right? Ruby. Ruby is basically gem, right? And this gem is chemically nothing but Al2O3. When you extract it from the nature, you will find the color of this gem is very dull. It is just a stone, so its color is very dull. If you want to sell with this color, then you will not get any value of the stone. You will not get any value of the gem. It is less costly. So to enhance its cost, so to enhance its value, what we do? We add a small amount of chromium into this ruby. We add a small amount of chromium. This chromium replaces few atoms of aluminum, and hence chromium is functioning like a defect in this ruby crystal. But the resulting material will have very shiny appearance, very bright appearance, because these chromium, manganese and cobalt, all these are coloring agents. So they give a very shiny appearance, very bright appearance to the gem, and hence the value of gem is enhanced. In tomorrow's class, I will be teaching you semiconductor. I will be telling you that the pure semiconductor has negligible practical utility because it has very small conductivity at the room temperature. So in order to enhance the conductivity of pure semiconductor, we add certain amount of impurity, like we add phosphorus, we add boron, etc. When we add impurity, then the conductivity of semiconductor increases many-fold. So in the semiconductor, we are willingly adding impurity to increase its conductivity or to decrease its resistivity. Whereas in ruby, we are adding chromium to increase its color, to enhance its color. So what my point is, sometimes we are willingly adding impurities to the material to change a particular property, either to upgrade it or to degrade it. So we need to understand these defects and we need to understand what is the impact of these defects on the material properties. Let us write few lines. I will not be writing, I will be dictating you. So after writing this, please write few lines and then we will be moving towards the further discussion. अखिलेश बेटा एक क्यूब लो, मान लो फ्रंट प्लेन का आपको चाहिए तो उसके पीछे वाले प्लेन पर ओरिजिन मान करके निकाल लो, ठीक, आपको मिल जाएगा 100। आपको पीछे वाले प्लेन का चाहिए, फ्रंट वाले पर ओरिजिन मान करके और एक्सिस डिफाइन कर लो XYZ, आपको फिर से मिल जाएगा 100। Please note down, natural crystals always contain different types of defects. Natural crystals always contain different types of defects. Due to uncontrolled conditions. due to uncontrolled conditions. Natural crystals always contain different types of defect due to uncontrolled conditions under which these crystals are formed. Under which these crystals are formed. Under which these crystals are formed. Full stop. Depending upon the type of defect, depending upon the type of defect and selected material, depending upon the type of defect and selected material, the certain properties in the material, the certain properties in the material, the certain properties in the material can be either improved, can be either improved or lowered, can be either improved or lowered, or lowered, full stop, or lowered, full stop. Next point. For example, for example, for example, the impurity of chromium, the impurity of chromium, the impurity of chromium in a ruby crystal, in a ruby crystal affects the color of the gem, affects the color of the gem, affects the color of the gem, thereby enhancing its value, thereby enhancing its value. For example, the impurity of chromium in a ruby crystal affects the color of the gem, thereby enhancing the value of the crystal. Full stop. Next चलते हैं. तो this is the crystal. Definition of crystal defect. किसी ने पिछली slide दिखाने को कहा है. Just quickly please take the pick of this slide so that we can move forward. Do it quickly. Hope it is done. All right. We are wanting to know what are the various types of defects. So these defects are classified according to their dimension. So classification of defects based upon dimensionality. Classification of defects based upon dimensionality, based upon dimensionality. Classification of defects based upon dimensionality. Their classification based upon dimension. The smallest defect can be like a point-like region, and point is considered zero-dimensional geometry. So such defects are called as zero-dimensional or point defect. Zero-dimensional or point defect. जीरो डायमेंशनल और पॉइंट डिफेक्ट्स में जैसे एग्जांपल के तौर पर वैकेंसी, इंटरस्टिशियल एटसेट्रा पढ़ेंगे आगे चल करके. vacancy, interstitial, etc. So only a point-like region is imperfect, remaining crystal is okay. Suppose this point-like region extends into a line. So such kind of defect is known as line defect. Yeah, one-dimensional defect. So the next one is one-dimensional or line defect or line defect. The examples of one-dimensional or line defects are dislocations. When you apply force and let us suppose one plane is dislocated, then a line defect would be found. So these dislocations are the example. So dislocations. There are several types of dislocation, not interested here, mechanical people may have studied. Then third one is, suppose the defect is extending throughout the surface of material. Like I talk about the free surface. Here are the atoms. So this is the end surface. End surface is known as what? Free surface. So this free surface is also a kind of defect. That is a surface defect. Or grain boundaries. In the one grain atoms have one orientation and in the other grain they have other orientation. So at the grain boundary periodic order is not followed. So those grain boundaries are also kind of defect. So we have two-dimensional or surface defect. Two-dimensional or surface defect or surface defect. So examples of this are free surface. Free surface means end surface, free surface, yeah, grain boundaries, etc. Since we are studying basics of material science, so we will be focusing ourselves only up to the point defect. Remaining all defects are being studied by the mechanical engineers in their technical syllabus or other branch engineers in their syllabus. Here in the basics of material science, I would be teaching you only the first defect, that is point defect. But time is not permitting today to take the new heading. So tomorrow I will be taking the first heading, that is point defect. Remaining two defects we will not be discussing. We would be discussing only point defect in this syllabus. So what is the point defect and what are the various types of point defect? That is the matter of discussion in tomorrow's topic. So today I am making the end of class here. We will be meeting you tomorrow at 9 o'clock. Thank you very much. Have a wonderful time. Someone said to repeat the last point. I am repeating it. Natural crystals always contain different types of defect due to uncontrolled conditions under which these crystals are formed. Depending upon the type of defect and selected material, the certain properties in the material can be either improved or lowered. Thank you.